Question 4, we're given a sample space that includes E1, E2, E3, E4, and E5. We then define events A, B, and C, where A is E1 and E2, B is E1, E3, E4, E5, and C is E2, E4. They give us the probability of these events occurring, but we really could have calculated it on our own. Because event A has 2 simple events in it, and there's 5 in the sample space, 2 divided by 5 would give me this 0.4. Similarly, 4 divided by 5 would give me 0.8, 2 divided by 5 would give me 0.4. They ask us to find the probabilities associated with the events by listing simple events in each. First one's a complement. When we do a complement, we look at the event and we can compare it to the sample space. Event A includes E2 and E3. What's left in the sample space then is E1, E4, and E5. To find the probability of this, we can take 3 simple events out of 5 events in the sample space, and that's going to tell us 0.6. We also could have gotten there a quicker way. The quicker way to get to the probability would be to say that if P of A equals 0.4, and the complement rule is 1 minus P of A equals P of A complement, 1 minus 0.4 also would have gotten us to this 0.6. When we see something like question part B, where it says we're looking for A intersect B, and upside down U means intersect, we should only count things that occur in both A and B. So here I see E3 is in both A and B. There's no other event that occurs in both. So the only event that counts here is E3. That means there's 1 event out of the 5 in the sample space that count, so it occurs with probability 0.2. For B intersects C, we're looking at these 2 lists. E2 and E4 are in C. E1, E3, E4, and E5 are in B. The only overlap is E4. So E4 is the simple event that's in the intersection. It occurs with probability 1 out of the 5 possible events, 0.2. Here, when we flip it the other way, this is a union, not an intersection. This means we're going to include everything in A, everything in B, and everything in both. We're just not going to double count the things in both. So if I look at B, I have E1, E3, E4, and E5. If I look at A, I have E2 and E3. Even if we don't count that E3 twice, we still have everything in the sample space. E1, E2, E3, E4, E5. So really, we would list everything here. E1, E2, E3, E4, E5. That means all 5 of the events fit out of 5 events, so it occurs with probability 1, or 100% of the time you get something that's either in list A, list B, or both. When we get down to part E here, this is a conditional probability. This is the first time where we have to worry about changing the denominator. Before, it was always out of what the total sample space is, 5 elements. When we see these conditional statements, it's going to be out of only the things after the conditional line. So part E asks us to do B given C. Here, when we go to do the probability, it's going to be out of the elements in C. Specifically, there's only 2 elements in C. So instead of dividing by 5 to find the probability, we're going to divide by 2, because the C is after the given line, meaning that's the total number of elements we're considering the sample space for this. On top, the numerator of this should be the overlap between B and C. E4 is the only overlap between B and C, so 1 out of 2 should be how we find the probability. That means it occurs with probability 0.5. Once I know C occurred, the chance of B also occurring is 50%, because really, if we chose E2, B didn't occur. If we choose E4, B did occur. Since these are equally likely, it's 50-50 that we also got something in B. What we list as the simple events is the 1 overlap event, in other words, E4. Now when we're doing A conditioned on B, in this case, since B comes after the given line, that's what we're looking at to see how many things should be in the sample space. B has 4 possibilities, so my probability is going to be out of 4. Of those 4 possibilities, the ones that are also in A is only this E3. So E3 is the event they have in common. It's one of the 4 events. That's why it occurs with probability 0.25. For parts G and H, we're back to where we're considering the entire sample space. For this union, when we keep unioning things, A, union B, union C, it's saying anything in any of these sets, just don't double count anything. So we previously knew that A union B included everything. Unioning C doesn't really matter. We already had all 5 of the events in just A and B. We can union C and get the same thing, but basically this includes E1, E2, E3, E4, and E5. So all 5 events are included out of 5. It occurs with probability 1. Last one here, A intersect B complement. It's a little confusing when we have 2 things at once, like an intersection with a complement outside of it. You kind of have to work through the parentheses. Basically what this is saying is look back to part B. In part B, this was the list of everything included in A intersect B. If we want the complement of that, we take this list, A intersect B, and compare it to the entire sample space. What's missing is everything except for event 3, in other words, E1, E2, E4, and E5. So if we take what we originally found as A intersect B and say find the complement of it, it's saying what's in the sample space that's not in A intersect B. So there were 4 things there out of 5 total. That's how we get probability of 0.8. Our complement rule still would have worked. If we look up here, A intersect B occurred with probability 0.2. If we did 1 minus that 0.2, that would also get us to this answer of 0.8.